Now, as we already discussed the isolated and non-isolated system, it's important to mention the conservative versus the non-conservative forces. There is forces in nature that are conservative and non-conservative forces as well. The difference between conservative and non-conservative. For the conservative, gravity and elastic forces act within systems without affecting the mechanical energy of that system, and those two forces are considered conservative forces. Means these forces doesn't affect if the system is isolated, it will stay isolated, it will not change or affect the nature of the system. It doesn't add or take away from the total amount of energy in that system. Other forces like friction and forces applied from outside of the system cause the energy of the system to change so that the energy is not conserved, which means those forces are non-conservative forces. So conservative versus non-conservative forces related directly to conservation of energy law. If this force affects the law of conservation of energy, then it's a non-conservative force. If it doesn't affect it, then it's a conservative force. Now let's talk about friction as a non-conservative force. We have the work for the friction. That's the work done, WF, by force of friction, the F friction on the system. So the W, we know that work equals F by delta D, but the W friction would equal the force of friction by delta D. And we know that the potential energy at the bottom of the ramp is the same when you have a certain road that is having kind of zigzag routes, then the bottom of the ramp would be having the same potential energy. So the loss in mechanical energy must be loss in kinetic energy. So friction is not a conservative force because it changed the conservation of energy for that system. And because the thermal energy is being radiated out of the system due to friction, the system is by definition a non-isolated system. The amount of work done by the friction caused the mechanical energy of the system to change. That can be represented mathematically as delta E mechanical would equal the work of friction. So if you split that down, E mechanical 2 minus E mechanical 1 would equal the work of friction, or E mechanical 2 would equal E mechanical 1 plus the work of friction. So EM2 would never equal EM1. So the mechanical energy at position 1 was different than the mechanical energy at position 2 due to friction. We know that in non-isolated system, the energy changes. Same as the example of the money in the room. You could have adding more energy or removing less energy. In this case, you could be adding energy or removing energy from the system. So the system is non-isolated. Not all external forces remove mechanical energy from the system. Motors in general used to add mechanical energy to a system. And if we take example as a ski lift motor, he increased the gravitational potential energy of the skiers. And if several external forces A, B, C, D, etc., as well as friction act on the system, then the total work done by all of these forces produce the change in mechanical energy. So E mechanical 2 would equal E mechanical 1 plus work, and can be equal to E mechanical 1 plus work by object A plus work by object B, work by friction, and so on. So this is another version of work energy theorem. If we want to draw the friction as he's acting on a non-isolated system to remove mechanical energy, we can draw position versus energy. We can see here mechanical energy is decreasing with position, and we can see here E potential started as high as possible and ended up as 0 by the end of the distance. And for kinetic energy, started as 0 and kept going all the way up. So rearranging the equation for the definition of work, we can say that delta E equals F by delta D. F equals delta E over delta D.